So let's look at example on Lagrange multiplier. A little bit more interesting than what we have done before. So here is a cantilever. It has a load at the tip. A dimension is length b, L, depth b, and height h. And in this case, the length is fixed, so it is not a variable. And the maximum deflection and maximum stress are specified. So in this case, I would like to minimize the weight of the cantilever. Because the length is fixed, it means that I would like to minimize find a combination of B and H that would minimize the weight without violating these constraints we have. So here is my problem. LBH is the volume, and it has these constraints. L minus L equals 0, so the specified value. S, this is my over I from your good old days. It is rectangular, so I just use the equation, and you have seen this before in mechanics of materials or machine design. 6PL over BH squared. For deflection, here is the equation. And here is after cleaning it. Of course, I know what is delta and what is S. So in this case, I have three variables and I have three constraints. So what we should get out of this? Remember, the thing we started at 4.1, we will have infinity cubic of possible solution. By adding three constraints, we are really talking about unique solution. But we'll see how it goes. Just like in 2D space, x1, x2, two constraint means unique solution. But we'll assume that I don't know this, and I am adding my constraint as lambda 1, lambda 2, lambda 3. And 6 variables I differentiate, and here is what I get. Looks a little bit intimidating, but hopefully not very much intimidating. These ones are just simple substitution. These three, I really didn't have to do differentiation. I can just take the three constraints and slap them here, there, and 4, 5, 6. So let's try to solve it. I will look at the fourth equation. It tells me that small l equal big L. So that's easy. It is explicit. I need to find B and H, and I can find B from the fifth equation in terms of H. And let's see how we can do that. So basically, we need to solve for the lambdas. And as we said, most probably, this is not a realistic optimization problem because it is unique solution. So let's go back and remove the constraint on the beam length and try to solve the problem. So now I have 5 constraints. 4 constraints. I'm just leaving the stress constraint. So here's a Lagrange. Here's my equations. And I will go third equation. I will expect B to be equal this. I will go back to the second equation, substitute n. So I can now have lambda 1 expressed. Go to the first equation with lambda 1. So here lambda 1, I replace it by this thing. I can solve for H. And this is what I know I need. I can go back and find, what do you think? You can use B from here because you know H. So you can find the better solutions this way. So Time for homework. That homework, which you do before class, is minimize x1 squared plus x2 minus 1, subject to minus 2x1 squared plus x2 equal 4. Sorry, I didn't notice that the quality is really terrible for this one, but it is in the book anyway. Uh, let's not do what he's doing. He said substitute a point, so disregard this. And in this case, basically, let's just minimize and see what's going on. In terms of another problem is this one. This is fairly similar, but it's a little bit of, interesting geometry thinking about it. So just to go to the standard formula and try to formulate your solution. This is also very standard problem. You have a box adjacent to the wall and you need to find the shortest ladder that can lean against the wall. So once you start drawing it, actually, yes, he gives you the drawing. You don't need it. You can draw it, sketch it yourself, and you find solution. In terms of after class homework, this is minimization problem, 3 variables. And I want you to do it with direct substitution because here it is explicit. Or you can use Lagrange multiplier and hopefully you will end with the same solution. This is neat problem, a tent, squarish tent, and you would like to find how you can make it to with the least amount of canvas. So I hope you'll find fun with this kind of problem. At least when I took the course, I really like this kind of problems. Hopefully you share my feeling. Thank you very much. Bye now.